study generating function. In previous lecture, we had defined generating functions and solved some simple examples. Today, we will solve some more examples. First of all, we will find the generating function of the for an equal to 5 raised per n minus 1 raised per n, 3 raised per n plus 8 raised per n plus 3cn for all the values of n. We know by the definition of generating function that the generating function is given by as equal to sigma n equal to 0 to infinity an s raised per n. So here as will be equal to sigma n equal to 0 to infinity, and an here is 5 raised per n minus 1 raised per n, 3 raised per n plus 8 raised per n plus 3cn sn. If we multiply each term by sn and write each term separately, then we get sigma n equal to 0 to infinity 5n into Sn plus sigma n equal to 0 to infinity minus 1 raised per n, 3 raised per n into Sn. Then sigma n equal to 0 to infinity 8n into Sn. Then sigma n equal to 0 to infinity 3Sn into Sn. So if we open these terms, we get for n equal to 0, 5 raised per 0, s raised per 0, which is 1. Then for n equal to 1, 5 raised per 1, s raised per 1 means 5s. For n equal to 2, 5 raised per 2, s raised per 2 means 5s whole square, and so on. Here for n equal to 0, 1. For n equal to 1, minus 1, 3 raised per 1, s raised per 1 means minus 3s. For n equal to 2, minus 1 whole square means plus 3 raised per 2, s raised per 2 means 3s whole square. Next term will be minus. So in this series, alternative term is positive and negative. For this, n equal to 0, 1, n equal to 1, 8s, n equal to 2, 8s whole square, and so on. Here for n equal to 0, 3c0, s raised per 0 is 1. Next is 3c1, s raised per 1, 3c2, s square, 3c3, s cube. So here these terms are same, and if you simplify it, 3c0 is 1, 3c1 is 3, 3c2 is 3 into 2 upon 1 into 2. 2 will cancel out, then 3s square, 3c3 is 1, so s cube. So here it is 1 plus 5s whole square, and so on. We can compare this series to be 1 plus x square plus x cube, and so on. In place of x, we have 5s here. So it is the expansion of 1 minus x raised per minus 1. So here in place of x, we have 5s. So it is 1 minus 5s raised per minus 1. Here the alternative terms are positive and negative. So this series can be compared to 1 minus x plus x square minus x cube plus x4, which is the expansion of 1 plus x raised per minus 1. Here x is equal to 3s. So 1 minus 3s plus 3s whole square minus dash 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 can be written as 1 plus 3s raised per minus 1, because x is equal to 3s here. Here all the terms are positive. So 1 minus 8s raised per minus 1. This series is similar to this series, and here x is 8s. And this is equal to 1 plus s whole cube. We can write it as 1 upon 1 minus 5s. We can write it as 1 upon 1 plus 3s. We can write it as 1 upon 1 minus 8s into 1 plus s whole cube. Now the LCM is 1 minus 5s, 1 plus 3s, 1 minus 8x. Here we have 1 minus 5s, so we will write 1 plus 3s into 1 minus 8s. Here it is 1 plus 3s, so if you divide it by 1 plus 3s, so we are left with 1 minus 5s into 1 minus 8s. In the numerator we have only 1, and here it is 1 minus 8s, so 1 minus 5s into 1 plus 3s, plus here in the denominator we have 1, and the numerator is 1 plus s whole cube. 1 plus s whole cube. So 1 plus s whole cube into 1 minus 5s into 1 plus 3s plus 1 minus 8s. If we multiply these two terms, these two terms, these two terms, these four terms, and add and subtract, then we get 120 s raised to power 6 plus 361 s raised to power 5 plus 367 s raised to power 4, 94 s cube minus 25 s square minus 27 s plus 4 upon 1 minus 5s, 1 plus 3s, 1 minus 8s. One more example, let C is equal to A into B, where an is the sequence an is equal to 2 raised to power n and bn is equal to 3 raised to power n and n is greater than equal to 0. Then we will learn how to find the generating function C in this case. This also I had explained in previous lecture that if C is equal to A star B, A into B and AS, BS and CS are generating functions of A, B and C respectively, then the generating function of C is given by CS equal to AS into BS. Here the sequence is 2 raised to power n, so generating function of 2 raised to power n is 1 upon 1 minus 2s. Here the sequence is 3 raised to power n, so generating function of this sequence is 1 upon 1 minus 3s. This also we have learned in previous lecture, how to find the generating function of the sequence of the type a raised to power n. If the sequence is 1 minus a raised to power n, then the generating function is 1 upon 1 minus as. So 1 minus 2s and 1 minus 3s. Now we will decompose it into partial fractions. So to decompose into partial fraction, let this is equal to alpha upon 1 minus 2s, which is first factor, plus beta upon 1 minus 3s, which is second factor. The LCM is 1 minus 2s into 1 minus 3s. So therefore this is equal to alpha into 1 minus 3s plus beta into 1 minus 2s upon 1 minus 2s into 1 minus 3s. On left hand side also the LCM is same. In the denominator we have the same term. So we can write 1 equal to alpha into 1 minus 3s plus beta into 1 minus 2s. Now we will find the values of these alpha and beta. So if 1 minus 2s, the term in the denominator is 0, then s is equal to 1 upon 2. If we substitute 1 minus 2s equal to 0, this term is 0. If we substitute 1 minus s2s equal to 0 means s equal to half here. So this is 3 upon 2 and 1 minus 3 upon 2 is minus 1 upon 2. So it means 1 equal to minus alpha by 2 or alpha equal to minus 2. To find the value of beta, we substitute 1 minus 3s equal to 0. 1 minus 3s equal to 0 means this term is 0 and s is equal to 1 upon 3. If we substitute s equal to 1 upon 3 here, so this is 2 upon 3, 1 minus 2 upon 3, 1 minus 2 upon 3 is 1 upon 3. So it is 1 equal to beta upon 3 means beta equal to 3. So if we substitute the values here, so it is minus 2 upon 1 minus 2s plus 3 upon 1 minus 3s. Hence the required generating function is minus 2 upon 1 minus 2s plus 3 upon 1 minus 3s. Now we will find numeric function of the generating function as equal to 1 upon 5 minus 6s plus s square. This is the given generating function. We are required to find the numeric function. So 5 minus 6x plus s square can be factorized into 5 minus s into 1 minus s. And if we decompose it into partial fractions, we write it as 1 upon 5 minus s into 1 minus s equal to alpha upon first factor plus beta upon second factor. First factor is 5 upon s, second factor is 1 minus s. So it means alpha into 1 minus s plus beta into 1 minus s is equal to 5 minus s equal to 1. To find the value of alpha, we substitute 5 minus s equal to 0. Means s equal to 5. This is 0, s equal to 5. 1 minus 5. Minus 4 alpha equal to 1. So alpha equal to minus 1 upon 4. If we substitute 1 minus s equal to 0, then s equal to 1. 1 minus s is 0. S equal to 1. 5 minus 1 is 4. 4 beta equal to 1 means beta equal to 1 upon 4. So it means as can be written as minus 1 upon 4, 1 upon 5 minus s, plus 1 upon 4, 1 upon 1 minus s. Alpha is minus 1 upon 4, beta is 1 upon 4. So we get this generating function. If we take 1 upon 4 common in this term, in second term, I have written it first because it has a positive sign and this has a negative sign. So I have uh, written second term first and first term at second place. If we take 5 common, so it will be 20, 5 4s are 20, and inside 5 upon 5 is 1 and minus s upon 5. 1 upon 1 minus s can be written as 1 minus s raised to minus 1. 1 upon 20, 1 minus s upon 5 can be written as 1 minus s upon 5 raised to power minus 1. Again, we know that this is the expression of the form 1 minus x raised to minus 1, 1 plus x square plus x cube plus x4 and so on. Here the coefficient of x raised to n is 1. Here in place of x we have s. So coefficient of s raised to n will be 1. Here the coefficient in place of x we have s upon 5. So coefficient of s upon 5 raised to n is 1. So the coefficient of s raised to n is 1 into 1 upon 4. 1 upon 4. Here 1 upon 20 into 1 upon 5 raised to n, because it was s upon 5 raised to n. So the coefficient of s raised to n will be 1 multiple of 1 upon 5 raised to n. So if we take 1 upon 4 common in these two, 1 upon 4, here we are left with 1, here we are left with 5. So 1 upon 5 into 1 upon 5 raised to n, 1 upon 5 raised to n plus 1. So this is the numeric function of this generating function. Now we will find the numeric function of as equal to 1 plus s whole square upon 1 minus s raised to power 4. We can write this generating function as 1 plus s whole square into 1 minus s whole raised to power minus 4. 1 plus s whole square is 1 plus 2s plus s square, and 1 minus s raised to power minus 4 is 1 plus 4s. We are using this binomial expansion. 1 minus x raised to power minus n is 1 plus nx minus n minus 1 upon factorial 2 minus x whole square is x square minus n minus 1 minus n minus 2 upon factorial 3 minus x whole cube is minus x cube and so on. So 1 plus 4 is minus 4 minus 5 is minus 4 minus 1 is minus 5. So 4 into 5 upon factorial 2 s square. This is minus 4 minus 4 minus 5 minus 4 minus 6. So 4, 5, 6 upon factorial 3 s cube and so on up to 4, 5, 6 n plus 3 upon factorial n s raised to power n. This is the nth term. Now we will multiply it by 1, then by 2s, then by s square each term, and write the like powers of s together. So for 1 we have only 1, then we have 4s, then 4 into 5 upon factorial 2 s square, then s square comes from here also, so it is 1 s square, then s cube 4, 5, 6 upon factorial 2 x cube. S cube will come from here also, s square into 4s plus 4 s cube and so on. So here to find the coefficient of s raised to power n, if you multiply it by 1, then it is 4, 5, 6 n plus 1 factorial n minus 2 upon sn. If we multiply it by 2s, then we will get s raised to power n plus 1 here. But we want the coefficient of s raised to power n. So we will write the previous term, which is 4, 5, 6 n plus 2 upon factorial n minus 1 sn. Previous term is, in place of n plus 3 we have n plus 2, in place of factorial n we have factorial n minus 1. And if you multiply by s square, then we will get s n plus 2 here. But we want the coefficient of s raised to power n. So we will write the two terms previous to this. So it means 4, 5, 6 n plus 3 upon factorial n s raised to power n. So these are the coefficient of s raised to power n. 4, 5, 6 n plus 3 upon factorial n, 2, 4, 5, 6 n plus 2 upon factorial n minus 1, 4, 5, 6 n plus 1 upon factorial n minus 2. Take this term common. If we take this common, here we have terms till n plus 3, but we have written till n plus 1. So here we are left with n plus 2 and n plus 3. Here it is factorial n, here it is factorial n plus n minus 2. So after n minus 2 we have n minus 1 and then we have n. So here we have terms n into n minus 1. Here it is 2. We have taken terms till n plus 1 common. So we have one more term after n plus 1 we have n plus 2. So this is n plus 2. Here it is factorial n minus 1. We have taken factorial n minus 2 common. So after factorial n minus 2 we have n minus 1 plus 1. Here we have taken outside, so 1. So 4, 5, 6 n plus 1 and factorial n minus 2. Here the LCM is n into n minus 1. This is n into n minus 1. So multiply these two, n square plus 5n plus 6. Here for this term, in the denominator we have n minus 1. So if you divide the LCM by n minus 1, we get n. And here we have 2n plus 4. 2n plus 4 into n. In the denominator we have no term, so n square minus n. N into n minus 1, n square minus n. If we multiply these terms and add, we get n square, 2n into n, 2n square and n square. N square, 2n square, n square, 4n square. This is 5n and this is 4n. 9n, 5 plus 4 is 9. Minus n, this is 8n. Here it is 6, so it is 6. And this is n minus 1 into factorial n minus 2. So this was factorial n minus 2. Here it is n minus 1, n. So I have written it factorial n. So here, if we take 2 common in this, if we take 2 common, then this 2, then 4, 5, 6, n plus 1, 2n square plus 4n plus 3 upon factorial n. So these are all the terms in continuation, 4, 5, 6, 7, 8 up to n plus 1, but 3 is missing. If we divide and multiply by 3, then 2, 3, 4, 5, 6 up to n plus 1. So we can write it as factorial n, and we are left with n plus 1, 2n square plus 4n plus 3 upon 3, because I have multiplied by 3 and divided by 3. So this is 3 factorial n. Factorial n will cancel out. So required numeric term is n plus 1, 2n square plus 4n plus 3 upon 3. Now we find the numeric function of the generating function as equal to 7s square upon 1 minus 2s into 1 plus 3s. So the given generating function can be written as 7s square. If we multiply these two, 1 plus s minus 6s square. Here the degree in the numerator is 2, degree in the denominator is also 2. Whenever the degree of the numerator is equal to or greater than the degree of denominator, we first divide the 2. If we divide 7s square by 1 plus s minus 6s square, we get minus 7 upon 6 plus 7 upon 6 into s plus 1 upon 1 plus s minus 6s square. If we again factorize it, we get minus 7 upon 6 plus 7 into s plus 1, 6, 1 minus 2s into 1 plus 3s. If we decompose into partial fractions, I have skipped the step here because you know how to decompose into partial fraction, as I have discussed in previous slide. A upon first factor plus b upon second factor, then find the values of constants. So minus 7 upon 6 plus 7 upon 6, 2 upon 5, 1 plus 3s plus 3 upon 5, 1 minus 2s. I have written this first and then second. So this is 7 upon 6 common. Here it is minus 1. 7 upon 6 common, 2 upon 5, 1 plus 3s raised to minus 1. Plus 3 upon 5, 1 minus 2s raised to minus 1. So 7 upon 6 minus what? Plus 2 upon 5. 1 plus x raised to minus 1. 1 minus x plus x square minus x cube plus x4. Means x in place of x we have 3s here. 1 minus 3s plus 3s whole square minus alternate terms will be positive and negative. And here it should be minus. Here 1 minus 2s raised to minus 1. So 1 plus 2s whole square and so on. 1 plus x raised to minus 1 is 1 minus x plus x square minus x cube plus x4, and 1 minus x raised to minus 1 is 1 plus x square plus x cube plus x4, and so on. Here all the terms are positive and negative. Here all the terms are positive. It means an is equal to 7 upon 6 into minus 1 plus 2 upon 5 plus 3 upon 5 if n is equal to 0. And 7 upon 6, 2 upon 5 into minus 3 raised per n means coefficient of s raised per n. 3 upon 5, 2 raised per n for n greater than or equal to 0. Here I have written the coefficient of a raised per s raised per n. Coefficient of s raised per n is minus 3 raised per n here, and coefficient of s raised per n is 2 raised per n here in this case. So this is the required numeric function corresponding to this given geometric function. Now one more example. Here in this example we will find the sum of this series using the generating function. The series is 1 plus 2 square plus 3 square plus 4 square plus n square and so on. We know that 1 upon 1 minus s is 1 plus s square plus s cube plus sn and so on, because this is the expansion of 1 minus s raised to minus 1. If we differentiate both sides with respect to s, derivative of this is 1 minus s raised to minus 1 is minus 1, 1 minus s raised to minus 2 into minus 1, means 1 upon 1 minus s whole square, and minus into minus will become plus. Derivative of 1 is 0, derivative of s is 1, derivative of s square is 2s, derivative of s cube is 3s square, derivative of s4 is 4s cube, and derivative of sn is nsn minus 1. If you multiply both sides by s upon 1 minus s whole square is equal to s, 2s square, 3s cube, and nsn. If we differentiate it with respect to s, we know how to differentiate the term of the form u upon v. We write the square of denominator, then denominator as it is, minus numerator as it is, derivative of denominator 2 into 1 minus s into minus 1. Here 1 minus s is common, so if in the denominator we are left with 1 minus s whole cube, and here it is 1 minus s, and 1 minus s is common, so minus is plus and 2s, so this is plus 2s, and so this is equal to 1 plus 2 square s, 3 square s square, and square s and minus 1, and so on. So this is 1 plus s. If you multiply both sides by s, then we get before 1 we have 0, so 0 square, 1 can be written as 1 square multiplied by s, 2 square s square, 3 square s cube, n square s raised to power n. I have multiplied both sides by s. If we multiply again this by 1 minus s, we get 1 minus s into 1 plus s upon 1 minus s whole cube, and 1 upon 1 minus s, expansion of 1 upon 1 minus s is this one. So 1 plus s square plus s cube plus s raised to power n and so on. And this is 0 square, 1 square s, 2 square s square, 3 square s cube and square s raised to power n. So this is s 1 plus s, and this is 1 minus s raised to power minus 4. 1 minus s into 1 minus s whole cube, 1 minus s raised to power 4. In the numerator it will become 1 minus s raised to power minus 4. If you multiply it by 1, then by s, then by s square, then by s cube, then by sn, and if we write the like powers of s together, we get 0 square, this one, then 0 square plus 1 square s, because if you multiply it by s, this is 0 square. If you multiply it by 1, then this is 1 square, the coefficient of s. For s square, here it is, if you multiply by 1, then this is 2 square. If you multiply by s, then this is 1 square. If you multiply by s square, then this is 0 square. So 0 square, 1 square, 2 square. So for s raised to power n, we will get 0 square, 1 square, 2 square plus 3 square plus n square and so on. But we know that the coefficient of s raised to power n in 1 minus s raised to power minus 4 is minus 4, minus 4, minus 1, minus 4, minus 2, minus 4, minus n plus 1 upon factorial n, and minus 1 raised to power n. So this is 4, 5, 6 and this is minus 3 minus n. If we take minus common in all, and this is minus 1 raised to power n, this is also minus 1 raised to power n, so it will become plus. So 4, 5, 6 n plus 3 upon factorial n. So this term I had written here directly in this particular question. 4, 5, 6 n plus 3 upon factorial n. This term. Here I had written directly, but here I have explained it how to find the coefficient of s raised to power n in 1 minus s raised to power 4. So this is 4, 5, 6 n plus 3 upon factorial n. So here the terms are starting with 4. If we divide and multiply by 1, 2, 3 and 1, 2, 3, then we get this term. Before n plus 3 we have n plus 2, then n plus 1, then n. So in the denominator, because we have multiplied by 1, 2, 3 and one more term we have factorial n. In the denominator, in the numerator we have 1, 2, 3, 4, 5, 6 n, n plus 1, n plus 2, n plus 3. So up to n we have factorial n. 1 to n means factorial n. So these terms will cancel out with factorial n. So we are left with n plus 1, n plus 2, n plus 3 upon 3 into 2 into 1, which is 6. So this is the coefficient of s raised to power n in 1 minus s raised to power 4. So if we, but this is the coefficient of s raised to power n 1 minus s raised to power 4. But we are multiplying this by s into 1 plus s. Means s into 1 plus s means s plus s square. Now the coefficient of s raised to power n here will be, in this expression will be, if we multiply it by s, then we will have s raised to power n plus 1, because this is the coefficient of s raised to power n. So this will be the coefficient of s raised to power n plus 1. But we want coefficient of n plus s raised to power n. So we will write one term before this term. So one term before this is n n plus 1, n plus 2 upon 6. Then this is s plus s square. If you multiply by s square, then uh, this will be the coefficient of s raised to power n plus 2. Because it is a coefficient of s raised to power n and we are multiplying it by s square, so we are getting the coefficient of s raised to power n plus 2. So, but we want coefficient of s raised to power n. So we will subtract 2 from each term to write the coefficient of s raised to power n. So this is n plus 1 minus 2, n minus 1, n plus 2 minus 2, n plus 3 minus 2, n plus 1 upon 6. So this is the coefficient of s raised to power n in this term. S into 1 plus s into 1 minus s raised to power minus 4. And this is the coefficient in 1 minus s raised to power minus 4. And on the right hand side, coefficient of x raised to power n is 0 square plus 1 square plus 2 square plus 3 square plus n square. So it means this is equal to 6 is the LCM, n into n plus 1 into n plus 2 plus n minus 1 and n plus 1. So what is common in the numerator? N and n plus 1. Here we are left with n plus 2, here we are left with n minus 1. So this is n plus n to n, 2 minus 1, 1. So n into n plus 1, 2n minus 6 upon 6. Now we will evaluate the sum of 3, 2, 1, 4, 3, 2 plus 5, 4, 3 plus n plus 1 and n plus 1 using the generating function. We know that 1 upon 1 minus s is 1 plus s square plus s cube plus sn and so on. Here these are the terms, not plus dash dash. So if we differentiate it with respect to s, we get 1 minus 1 upon 1 minus s whole square, because its derivative is minus 1 1 minus s raised to power minus 2 into minus 1, and minus and minus will become plus. So 1 minus s raised to power minus 2 means 1 upon 1 minus s whole square. Derivative of 1 is 0, derivative of s is 1, derivative of s square 2s, derivative of s cube 3s squared, and so on. Derivative of sn is ns minus 1. Again differentiated with respect to s. So derivative of this is minus 2, 1 minus s raised to power minus 3 into minus 1. Minus 2 into minus 1 is 2 and 1 minus s raised to power minus 3. So it means 2 upon 1 minus s raised to power 3. And derivative of 1 is 0, derivative of 2s is 2, derivative of 3s square is 3 into 2s. Derivative of 4s cube is 4 into 3s square. And derivative of ns minus 1 is n into n minus 1 s raised to power n minus 2. And its derivative is n plus 1 n s raised to power n minus 1. And next term will be by symmetry n plus 2 into n plus 1 into s raised to power n. So here if we differentiate once more, we get derivative of this 2 upon 3, 1 minus s raised to power 4. Derivative of this is 0, derivative of this is 3 to 1, derivative of this is 4, 3 to s, derivative of next term will be 5, 4, 3 s square, derivative of this is n plus 2, n plus 1, n, sn minus 1, next will be n plus 3, n plus 2, n plus 1 s raised to power n. This I have written by symmetry because see the term patterns 3 2 1, 4 3 2, 5 4 3, n plus 2, n plus 1, 1, n. So here it will be n plus 3, n plus 2, n plus 1, s raised to power n. If we multiply both sides by s square, we get 6, 2 into 3 is 6 s square, 1 minus s4, 3 2 1 s square, 4 3 2 s cube, 5 4 3 s4, and then n plus 1, n minus 1 will be Sn, n plus 2, n plus 1, n. We are multiplying it by s square. So it will be n Sn plus 1 and next will be n plus 3, n plus 2, n plus 1, Sn into s square. Sn plus 2. So this multiplied by s square is this multiplied by s square is this, and I have written one more term previous to this term by symmetry. So here, if we multiply both sides by 1 minus s, we get 1 upon 1 minus s, 6s square upon 1 minus s raised to power 4. And 1 upon 1 minus s is 1 plus s square plus x cube plus s and so on into this term. 3 2 1 s square, 4 3 2 s cube, 5 4 3 s cube, and so on up to n plus 1 and n minus 1 Sn, n plus 2, n plus 1, n Sn plus 1, n plus 3, n plus 2, n plus 1, Sn plus 2. Now the coefficient of 6s square upon 1 minus s5 is equal to the coefficient of s raised to power n minus 2 in 6 upon 1 minus s5, because this is the coefficient of s raised to power n. We are multiplying it by s square. So the coefficient of Sn minus 2 in this will be same as coefficient of Sn in this term. Here it was 1 minus n to 1 minus s raised to power 4. So I have written 1 minus s raised to power 5. So the coefficient will be 6 into 5 into n plus 2 upon factorial n minus 2. 6 is this term, and if you expand the coefficient of nth term will be 5, 6, 7 up to n plus 2 upon factorial n minus 2. Here it is 6 and the rest of the terms are starting with 5. So I am multiplying by 1, 2, 3, 4 and dividing by 1, 2, 3, 4. So this is nothing but factorial n plus 2, and this is 6, and this is the factorial 4, and this is factorial n minus 2. It is not dash dash, but it is 1, 2, 3, 4 into factorial n minus 2. We have multiplied by 1, 2, 3, 4 and divided by 1, 2, 3, 4, and already we have factorial n minus 2. So this side, the coefficient of s raised to power n is 3, 2, 1 plus 4, 3, 2 plus 5, 4, 3 plus dash dash n plus 1 n into n plus 1, 6 factorial n plus 2 factorial 4 factorial n minus 2. Thank you.